Welcome to another lecture of our automata playlist. Today we are going to learn about a new thing, that is a pushdown automata. So what is a pushdown automata? We already know what is regular expressions and what is context free language or context free grammar. So we know that we can express any regular expression or regular language through a finite automata, but we cannot construct a finite automata for every context free language. Okay, so for that purpose we need one automata which is more powerful than a finite automata. So to describe or to show the machines which can accept the context free languages, we need a powerful automata that is known as pushdown automata. So pushdown automata is more powerful than a finite automata. So what is extra here? Here we have a memory element, that is a stack. So see, this is more powerful machine. Why? Because along with finite automata we have a stack here. Okay, so finite automata plus stack equals to PDA or pushdown automata. So as we know that regular expressions are accepted by both NFA and DFA, so CFG also accepted by pushdown automata here. So here we already know that regular expressions are accepted by NFA and DFA. We already know that we can convert NFA to DFA, but for pushdown automata we cannot convert a DPDA, that is a deterministic pushdown automata, and a non-deterministic pushdown automata NPDA. We cannot convert them. Okay, these are not interconvertible. So these two are separate from each other. Okay, so now let's see an example. So that's how we denote it. So this is our input symbol. Okay, here we are, our input symbols or input alphabets are written, and this is our stack, that is the memory. So here we push something on top of the stack, and sometimes we pop this from the top of the stack. When do we push and when do we pop, that we are going to learn later, but for now that's the stack we will use in our PDA. And this Z0 is our stack symbol. So this is our finite control. This thing is our read write head. This reads our input symbol from left to right in this manner, and this also reads the top of stack value, and according to the top of stack input symbol and our current state, depending on all these three factors, our next state is determined, and after that it moves from our current input symbol to our next input symbol. And also if we push anything into our stack, then our stack head is going upper, that is for the top value. We only work on the top value for the stack. Okay, so now let's see what are the definition of our PDA. So obviously PDA is a more powerful than finite automata because we have a memory element here. So now let's see what is the definition. Here are 7 tuples, that Q is the finite set of states. This is these type of things are similar. There are a few things that are new. So you already know that Q is finite set of states, and this is the input symbols. Okay, but here this tau is new. So this tau means the stack alphabet, whatever we push in our stack. So see here, this input symbol and stack alphabet is not always same. Suppose for this automata, here we have similar number of zeros and ones. So whenever we are reading a 0, we are pushing that 0 into our stack, but that does not mean whenever we are reading 1 we have to again push 1. Okay, so whenever we are reading 0 we are pushing 0 into stack, but whenever we are reading 1 we pop that 1, sorry there is no 1, so we pop that 0 from our stack. Okay, so the number of zeros which we push in the stack will be equal to the number of zeros we pop from the stack. So we push for 0 and pop for 1, so this means that 0 and 1 will be equal. So here for that particular example, the input symbol will contain both 0 and 1, but the stack symbol will contain only 0, and this is our transition function. We write it like this. Okay, so for Q is our current state or the set of states actually. So our current states and depends. So this is our set of states actually, and this is our input symbol along with null. so there can be any input symbol also null, and the tau, that is stack alphabet. So these three things together determine our next state. Okay, so here are three cases possible for transition function. I am coming to that later. So, and this q naught is our initial state, z naught is our stack start symbol, that is I have already shown you here. You can also write marking dollar or anything we want, this is our choice completely. And this f is the set of final states. Okay, so here is an example. So this is our language or context free language. So here it is like L equals to 0 to the power n, there is a symbol that is hash, and 1 to the power n, and n is greater than equal to 0. So how can we design that? So see, for all the zeros we will push something in the stack, and whenever we are having 1 in our stack we will start popping it out. Okay, so this will accept our language. So let's see. So now this is our starting state or initial state, this arrow denotes it, and from this state we are going to another state through this transition. Okay, so here the transition function is null, null, and this is our stack symbol marking dollar here. So our inputs alphabet is null, also our stack top having null, and we are pushing in this symbol, that is our stack top marking dollar symbol in our stack. So that's how we read it. Okay, this is our input symbol, this is our stack top, and this is what we are pushing inside stack. Okay, so now we are pushing just marking dollar in our stack, this will denote the end of stack. Now inside this step we are having a self loop, because there can be any number of zeros, so we are having a self loop for 0. So our input symbol we are reading 0, and from stack top we are reading null, and we are replacing this null with the input stack symbol a. Okay, so this means whatever I have already told you here. Okay, this for this case we are pushing in a stack. So when we are pushing in a stack, when we are reading null from the stack, but we are having something in our stack after the transition. So we are reading null from the stack, but after we are reading 0, we have a inside our stack. So whenever we are having 0 in our input symbol, we are pushing a into our stack. So suppose if the string was like this 0 0 hashtag 1 1, then for this 0 we are pushing a, and for again for self loop this 0 we are again pushing a inside our stack. So this is our stack. So suppose for here we are having dollar, for first 0 we are pushing a, and also for second 0 we are again pushing a into our stack. Okay, and now what we have? Now we have a hash. So for input symbol hash we are reading null from our stack top, and we are replacing it with null. This means we are neither pushing nor popping. So I have already told you this case, if the both and stack symbol before and after transition is null, and this means we are neither pushing or nor popping anything. Okay, so this hash is also now done. So now read write head goes to hash, and now our read write head moves to this one. So now comes here, there is a self loop for 1 also. So whenever in our input symbol we have 1, and in the stack head we are having a, in the stack top we are having a, we are replacing this a with null. This means we are popping this a. So here for the first one we are popping this a out, and for the second one we are also popping this a out. Okay, so now our string is completed. Now we only have a marking dollar, that is our stack symbol. So now we are reading null from our input string, and we are having a marking dollar in our stack already, so we are replacing this marking dollar with null. So now our stack is also empty. So now we have reached our final state. So this is a DPDA which we have designed. So see, I have also written here for, so see this is our stack symbol, and here we are for every symbol 0 we are, and for the stack symbol null or the stack top null, we are pushing a inside the stack. So we are pushing a in the stack for every 0 we read. Okay, so for every 0 we read in our input symbol, we are pushing a, and here what we are doing, here we are popping a from the stack top for every 1 we read. So this ensures that the number of zeros and number of ones before and after the hash symbol is always same. Okay, so this is the DPDA, required DPDA. So now let's check. Here we do not have any hash symbol. So here how should we do that? So now let's see. So for this transition again, we are having what? We are going to another state. We are going to another state, and for which what is the transition? So first we are just pushing the stack top here. Okay, so this is our stack symbol. We are pushing it inside our stack. Now again, for every zero, we are doing what? We are reading the 0 from our input symbol, and we are reading null from our stack top, and we are pushing A inside our stack. Okay, so now here we do not have any hash. Okay, but whenever we are having our first one, this means after that there can be no zeros. Okay, so whenever we are getting a single one, after that all there is only one. So we will make this transition for 1. Okay, so this transition will happen for input symbol 1, and for 1 what we will do? To ensure the number of zeros and ones, we need to pop whatever we are pushing for 0, we need to pop that for 1. So what will be there inside our stack top? There is A, and we are popping it and replacing it with null. Okay, and also if there was only a single one, then this will work, but there can be any number of ones, as we know that n is greater than equals to 0. It can be 5, 6, 7 also. So we are doing what? We are popping it. Okay, so we are popping it, and we are having what? We are again just the similar thing. Okay, for 1 we are popping A and replacing this A with null, and now all the string is accepted, and now we will just remove the stack top and reach our final state. Okay, so the stack top is, we are reading null from our input string, and we are removing our marking dollar symbol and replacing it with null. So this is the PDA.